Okay, welcome everyone. I'm John Niebuhr, and I'd like to welcome everybody to this WRS seminar today. Today we have Dr. Chuck Regan from the Minnesota Pollution Control Agency here to give a presentation. He is currently Senior Research Scientist with the Minnesota Pollution Control Agency and has a degree in geology from Colgate University, Bachelor of Arts, Colgate University, and then master's and PhD from the University of Minnesota, also in geology. Chuck has been at the center of the effort to develop HSPF model, that's a hydrological simulation program, FORTRAN, for the state of Minnesota at the Minnesota Pollution Control Agency. That model has been used to, or is being used as a way of evaluating the pollution loads in rivers coming from land uses as well as from point sources. And his effort has, this model then serves as a tool that can be used for allocating these loads to try to figure out how to reduce the loads in the rivers. So it has to do with the TMDL program. The model has, I'm going to steal some of Chuck's story here probably, but the model has been developed for essentially nearly all of the Huck 8 watersheds in the state, and there are 82 of those, if I get the number correct. Chuck can correct me, I guess. But so these models have been developed by consultants, and Chuck had the responsibility to work with them, check these models out to make sure they're doing what they're supposed to do. I'm going to leave it to Chuck to give the whole story, because he's the one that knows what it is. But thank you, Chuck, for coming, and appreciate you taking the time to make this presentation today.
Great. Well, thank you, John, and thank you, Dr. Muller, for having me. I appreciate the opportunity to talk to your students and other interested parties. Please interrupt me if you have questions. And I should also warn you, I do have slides with a lot of information. I put those together more as a resource for people who might want to read them later. So don't feel like you have to read every word on every slide. And I'm going to go through quite a few things, but not in any level of detail. But again, if you have questions or something doesn't make sense, please don't hesitate to stop me. This is really for your benefit. So I want you to get the most out of it that you possibly can. So I'll touch on models and tools in Minnesota, some model characteristics, needs that the MPCA has that can be met with a watershed model, some basics of the model itself, the hydrologic simulation program, FORTRAN, as John alluded to, the history of the development of HSPF, some HSPF model attributes, the use of HSPF at the MPCA, HSPF input requirements, talk a little bit about the guidance document that we use for the development of HSPF models for use at the MPCA. And then I'll talk a little bit about the status of the model statewide, and if time allows, I can touch on a few case studies. So first, I want to acknowledge that in the state of Minnesota, there's a lot of different entities using different models for different purposes. And so, for instance, at the PCA, we use a very simple lake model called Bathtub, which is a receiving water model to get our lake TMDLs done. And I'm going to just take a second here just to explain a little bit about TMDLs. The federal government requires us to classify water bodies for designated uses. And then we develop standards, water quality standards for each designated use. And if a particular water body doesn't meet the standards for its designated use, then the state, which is me, has to complete a total maximum daily load allocation study. So when you hear the words TMDL, it's basically a federal mandate that requires the state to come up with an estimated reduction for a particular pollutant so that that water body can meet the standards for its designated use. So hopefully now you'll understand a little bit about why we have to do TMDLs. And I'll get back to this figure here. The Corps, the Federal Army Corps of Engineers uses these HEC models to designate floodplains and to delineate areas of floodplains where you're not allowed to build and determine insurance rates if you do build in a floodplain. For people who are interested in citing agricultural BMPs, we have some site scale models and tools. The Department of Natural Resources uses a gridded model to cite and look at the effectiveness of BMPs. There's also two other tools, the Agricultural Conservation Planning Framework and the Prioritized Target and Measure applications. Those are both tools that leverage GIS to help cite agricultural BMPs on a field. And then we're using a watershed model called HSPF, which simulates the runoff and movement of water, sediment, and nutrients from the land surface to a receiving water body. And also at the University of Minnesota, Dr. Mulla and some of his colleagues use a soil and water assessment tool. So people ask me, why are there so many different models and what makes them different and how can we kind of think about them and classify them? And so one way I look at models is I look at three basic characteristics. And the first one I look at is spatial resolution, which is the precision with which features are represented on the land surface. Now in Minnesota, we have what's called LIDAR, light detection and ranging. That's a coverage that has 1 meter. It's basically a map of the Earth's surface that has a precision of 1 meter in the XY coordinates. And that's really leveraged in those tools like PCMAP and ACPF that are really, you need that spatial resolution if you're going to cite BMPs on the ground. In our watershed models, we use those LIDAR datas, the LIDAR coverages, but then we do some statistical analysis to summarize the important spatial relationships. And so we don't migrate the whole LIDAR coverage into our watershed model, but we do some statistical massaging of the LIDAR coverage and bring that into our modeling environments. The next characteristic is temporal resolution, which is the frequency at which a model reads input and generates output. So at the simplest end of the spectrum, we have steady state models like Bathtub, which we use, which time isn't varying. We're simulating one condition, and it's usually either an average condition or the worst case condition. But time doesn't vary in steady state models. Where continuous simulation models, and we'll get into more of this, they read inputs and they read inputs over time. And so we have continuous simulation models that read annual inputs, monthly inputs, daily inputs. There's even a stormwater model in the city of Austin that runs on a 1 second time step. Now you have to be aware that in order to generate meaningful outputs at a 1 second time step, you need meaningful inputs at a 1 second time step. And Austin actually does that. It measures rainfall every second. So as your resolution goes up, your data inputs become more onerous. And the last concept about models is called process representation. And This is basically getting at what quantity are you trying to predict or simulate, and what are the processes that have a big impact on that quantity. So one example would be if you wanted to predict how much you're going to weigh a month from now, you'd probably want to include in your model how much you weigh today, what you plan on eating over the next month, how much you plan on exercising the next month. But you probably don't need to include the color of your car, or what side of the street you live on, or what color socks you're wearing. Those are probably processes or factors that have minimal or no impact. So a good model or an efficient model will purposely include the processes that affect the quantities of interest and purposely exclude things that have minor or no impacts. So one of the developers of HSPF is Tony Denigian, and he always says models are the cartoons of reality. And so one of the things we want our models to do for us is we don't want them to be burdened by all the details of reality, but we want them to include the important processes and characteristics so that they're recognizable. And models can have different levels of detail. Some might be more simple than others, but ideally, they're all recognizable and capture the main characteristics. And I'll talk about this more, but we want to use the simplest model that meets our needs. And so a couple of things I'd want to bring up is I hear from people all the time, we have a model, we don't need another one. Well, I think that arises from an expectation that one model should be able to answer all your questions, solve all your problems, do all your jobs for them. And so I remind people, just because you have a really good hammer doesn't mean you'll never need a screwdriver. And so one of the good characteristics of kind of experienced modelers is they'll identify the questions and problems that need to be solved, and then look at and choose the best model to answer that question. Often inexperienced modelers will just choose the model they're most familiar with, but you really need to choose the best tool for the job. And a professor at Yale University in the late 1800s, J. Willard Gibbs, says you should use the level of complexity required to properly define the system, but no more. So you want to have enough detail and enough representation to answer the question, but you don't want to have excessive superfluous detail that really isn't going to do you any good. It's not efficient. So for instance, for spatial resolution, you might need a lot of spatial resolution to site BMPs on the ground, but you might not need that same level of spatial resolution to predict water quality in a large river. And so the PCA, what our needs are, we're required by the EPA to do those TMDL studies. And so the conventional parameter like sediment, where we're trying to limit a pollutant, I spend a lot of time on that. I spend a lot of time on dissolved oxygen TMDL studies. That's a little different because dissolved oxygen is not a pollutant. We're actually trying to maintain high levels of dissolved oxygen. So we're trying to limit things that would lower our dissolved oxygen levels. And then I also do nutrient criteria compliance, which we're trying to not get excessive levels of total phosphorus, biochemical oxygen demand, chlorophyll A, pH, DO fluctuation. And I also work with point source staff to set total phosphorus effluent limits. So these are all regulatory tasks that we're required to do by the federal government. So this is why we're using, this is really our needs. And here's a conceptual model representation of a watershed model. So up here across the top, we have these dynamic meteorological inputs, and the sun comes up and down every day. That's rather predictable, but precipitation is a lot less predictable. When it does rain, some of that rain might fall directly on a reach, but most of it will fall on a land area. And that land area, if there's enough to cause runoff, that will take with the water, it will carry sediment and nutrients with it to the stream. We add in our point source contributions, And HSPF, in addition to doing simple channel routing, it'll include some critical in-stream processes in the representation. And so another reason to say why we need a watershed model is we have a great monitoring program in Minnesota, one of the best in the country, one of the most extensive in the country, but we can't model for everything all the time, everywhere. And the problem is we have more impairments than we have monitoring sites. So we need a way to extrapolate the great monitoring data that we have, extrapolate and interpolate in space and in time. And also our watershed models allow us to go back in the past, and during times when we had an impairment, we can change some of the input conditions to see what it would have taken to not have had the impairment at that time. And another reason why we're using a watershed model is 20 years ago when we started doing TMDLs, we were doing them one at a time, and it was costing too much and it was taking too long. And my former division director used to say, at the rate we're going, it's going to take us 100 years to get our TMDLs done. And I corrected him, and I pointed out, no, at the rate that we're going, it's going to take us 300 years. And I kind of pointed out to him that, you know, at the rate we're going, Lake Pepin will be filled in with sediment by the time we get the Lake Pepin sediment TMDL done, which some people thought that was humorous. He did not. But regardless, now we're doing all our TMDLs on a Huck 8 scale. So as John said, there's about 80 of them in Minnesota, roughly. And so instead of doing TMDLs one at a time, we're doing them 50 at a time. And we're getting them done cheaper, and we're getting them done more quickly. And so a few things about the HSPF model. It is a continuous simulation model. We're running on an hourly time step in Minnesota. It represents different land uses with the same level of detail. It includes surface and subsurface hydrology, stream and lake hydraulics, and also some critical processes like nutrient cycling, which it's critical if we're going to do dissolved oxygen evaluation. We need the temporal resolution of an hourly time step and the process representation of nutrient cycling. And so HSPF is the core watershed model in EPA's modeling platform called Basins. It's also in the Corps of Engineers watershed modeling system. It was one of the models used as part of the Chesapeake Bay watershed model. It was coupled with some more complex tidal estuary models. It includes in-channel sediment processes. Unlike other models, it lets you include individual particle sizes. And again, it includes those critical processes of algal respiration, photosynthesis, growth, death, nutrient uptake, and subsequent release. So HSPF divides the physical world into three areas. There's impervious surfaces that when it rains, you generate surface runoff. You have pervious surfaces that generate surface runoff, but also shallow and deep groundwater. In the lakes and streams, you have a representation of your inorganic nutrients that can be basically eaten by algae. And that then when algae die, they become part of organic sources of organic nitrogen and phosphorus. There are modules that allow the bed to interact with the water column, and all of this is going on as water is flowing downstream. So a little bit about how HSPF came to be. You can trace its origin back to the great-grandfather of HSPF. Norm Crawford developed the Stanford watershed model, which is the hydrology section of HSPF, in his 1960 PhD thesis. So that's 60 years ago. He introduced the civil engineering community to continuous hydrologic modeling. Before that, most things were just either steady state or transient, but he introduced continuous hydrologic modeling. There was also a model called the Hydrocomp simulation program and another model called the agricultural runoff management model. And so EPA integrated the HSPF, HSP model, the ARM model, and another model called the non-point source pollutant loading model, and integrated that. And the first version of HSPF was released in 1980, and the USGS supports it, as well as many of its utilities. EPA supports it. It's in that basins package. I should mention it's a FORTRAN model. It runs in the DOS environment, but now we do have a Windows interface called WinHSPF. The main advantages of using HSPF, first and foremost, is EPA mandates that we do TMDLs, and they developed HSPF to expedite the development of TMDLs. So if we're doing TMDLs because EPA says we have to, it makes sense that we use a tool that they recommend. So that's the biggest reason. There's very strong code control because HSPF is used for regulatory purposes to set effluent limits for point sources. So we don't want the user community to find errors. We want to find all those errors before there's a release, because it would be very stressful if we had different versions of the model giving us different answers with the same input. We don't want that. There's a lot of detail in the in-channel representation geometrically, and there's also a lot of good detail in the biochemical processing. And we have that temporal resolution, which is really strong for DO and helping us generate runoff. You can use it for hydrograph studies. It's approved. It's flexible. If there's a process you want to represent that isn't there, you can write a special action and get that in there. It's also been through the courts, and it's been vetted, and it has prevailed every time in the Chesapeake Bay, Anacostia River, and Connecticut River. So at the PCA back in 1985, EPA said we had to develop a waste load allocation for the wastewater treatment plants in Minneapolis and St. Paul. We knew we needed, after that study, a 40% reduction in biochemical oxygen demanding materials from upstream sources, mostly in the Minnesota River. Experts got together and said, let's use HSPF. In 1988, we got a grant from the Legislative Commission on Minnesota Resources to get started. In 96, we used HSPF in the lower Minnesota DO TMDL, and then we used it again in 03 for the turbidity TMDL. And in 06, we decided to apply HSPF outside the Minnesota River Basin. And in 08, we had the Clean Water Legacy Amendment that provided additional funding for HSPF applications statewide. And so the types of data we need to build an HSPF model, we can divide into 4 categories. The first is the very dynamic forcing functions that are our meteorological inputs. Hourly inputs are required for our application. For the watershed area characteristics, we can glean much of what we need from GIS layers. For the configuration of the drainage network, we can get a lot of information about lakes and rivers from the DNR. And then lastly, we like to get a lot of measured observed data, which we use to compare against the model output. Because we want to convince ourselves that if where we have data, the model can match it, then maybe we can trust the model where we don't have any data. So as far as the forcing functions go, we've migrated to gridded meteorological inputs. NASA has developed the North American Land Data Assimilation System. And what that gives us is, going back to the late 70s, we have on a grid of 15 by 15, we have hourly precip rainfall amounts, for every hour since the late 70s. So that's really been helpful. There's also a product developed by Oregon State. It's only on a daily time step, but the grid is finer. So we use those 2 products in tandem. And then also PRISM has some other important coverages for solar radiation, wind speed, air temperature, things that are really important, again, if you're worried about dissolved oxygen. We include wet and dry atmospheric deposition, and we include our contributions from our major and minor point sources. So we have to add those into the model. Otherwise, we'd overestimate our non-point contributions. For watershed characteristics, we use a lot of GIS layers, as I mentioned. We have a digital elevation model that's based on LiDAR that the DNR hydrologically corrected, that comes with a sub-watershed boundary layer, a hydrography layer. We use different land use layers and soil type layers and boundaries of our cities and point source locations. In agricultural areas, we'll try to leverage information from tillage transects, fertilizer application rates, tile density. Forested area, we have some coverages for logging practices and old growth. And we also try to leverage any other helpful information from sediment budgets, sediment fingerprinting data, other existing models we'll definitely take a look at. For the drainage network, we want to get as many surveyed cross sections and rating curves as we can. We use a lot of the HEC models in the bigger rivers or wherever they exist. And for the lakes, the DNR provides a lot of great lake bathymetry data, as well as lake level elevation and geometry information. And we got to be aware of things that would impact flows like dam manipulation or mining pits that are being dewatered. They'll obviously affect flow. For calibration, we want to compare our model outputs with measured stream flow measurements, lake level measurements. We have some coverages for snow depth and evapotranspiration, so we want to compare our model with those. We want to compare our simulated sediment information with measured sediment information, likewise with water quality information. We want to make sure we look at SON data for water temperature and dissolved oxygen, because those vary throughout the course of a day greatly. We compare our loads with other load estimator products like Flux and LoadEst. We use a weight of evidence approach. We look at the non-point loading rates from every land use in the model, and then we create little budgets for every land use and every reach in the model for water, sediment, all the nutrients. We conduct statistical comparisons of measured versus simulated flows, and we do a lot of point-to-point comparisons for water quality. We do some time integrated work, again, comparing with load estimators and paying particular care with hourly dissolved oxygen and hourly temperature values. So when we calibrate an HSPF model, we have to follow this sequence because things are built on top of each other. So we start with flow, then water temperature, sediment, then nutrients, then oxygen demand, chlorophyll A, and lastly, dissolved oxygen. So in order to do well for dissolved oxygen, you want to do well with everything above it. And we have a guidance document which has some guidelines for comparing simulated versus observed flows, and we have criteria that the models need to meet before we use it in a TMDL study. So just want to throw this out that many years ago, a government organization put together the Anacostia River TMDL, and they used annual loads. And environmental groups sued and said, when you use an annual load, you miss out the impact of storm events, which can affect daily loads quite a bit, but you're not going to detect a storm event in an annual load. So the environmental group sued, and I forget the judge's name, but her ruling, she said, daily means daily. So we need to be able to look at things on a daily scale. We just can't look at things on an annual scale. And so I'll give maybe a couple of examples of how that's important. When we're worried about sediment transport, that's driven by surface runoff, and surface runoff is driven by rainfall intensity. And so HSPF can pick up on that because it uses an hourly infiltration index approach. And what I have along the bottom here is 24 hourly rain gauges, and every hour HSPF will check for precip inputs and antecedent moisture conditions, and if warranted, will generate surface runoff. So in a low intensity event, we'll have a bare dry field. We have an infiltration capacity of 0.1 inches, which is really reasonable. That's a reasonable number for Minnesota, a lot of the soil types we have. So if we had a low intensity event where we drizzled 1/20th of an inch for 20 hours, would have a daily rainfall of 1 inch. But our infiltration capacity is never exceeded. We have no sediment runoff, and therefore no surface runoff, no water runoff, no sediment wash off. Now, if I have a high intensity event, I have the same conditions before, same infiltration capacity, but all the water comes down in an hour. And so I can infiltrate the 0.1 inches, but now I've got 0.9 inches that generate surface runoff and can wash off sediment. So if I'm running on a daily time step, all I have is 1 inch per day. It's the same. The temporal resolution doesn't allow me to distinguish between those two events. And so that's going to make it difficult to predict storm events, and you can't accurately calibrate to all types of events. So with the hourly time step, I can distinguish between those two events. The low intensity event doesn't generate any runoff or sediment. The high intensity event does. Using a daily time step, I can't distinguish between the two. So usually what people do is they shoot for the middle, which leads to a overestimation of low intensity events, underestimation of high intensity events. And that's a problem. This is a problem because TMDLs are, largely driven by storm events. So we don't want a systematic underestimation of high intensity events. So here's just a quick example. I used the Pomme to Terre HSPF model. I actually built this one myself, and I used it to take on 17 turbidity TMDLs. The lake TMDLs, we used HSPF output as bathtub input. All of the reaches, they didn't have a gauge close by, so we used HSPF simulated flows to generate flow duration curves. And we followed EPA's guidance of calculating load capacity for each flow zone. And we calculated the percent sediment reduction needed for each flow zone. And so we were able to develop a load duration curve, which is really just multiplying the flows from HSPF by the water quality standard. And that enabled us to develop the TMDL. Jumping over to dissolved oxygen, which we have a lot of dissolved oxygen impairments. This is actually 24 dissolved oxygen concentrations from the Little Cobb in the LeSueur watershed. And you'll notice that at sunset, the dissolved oxygen concentrations start to fall, and they continue to fall until about sunrise. And the reason for this is algae consume oxygen all the time. But during daylight hours, they produce oxygen, and they produce oxygen at 2 or 3 times the amount they consume it. So they cause DO to fall at night and rise during the day. Now we have a dissolved oxygen minimum standard. We can't go below 5. So we're violating that standard here. We also have, as part of the eutrophication standard, the difference from the maximum to the minimum can't exceed 5 milligrams per liter. Well, here it's about 8 or 9. So we're violating that standard as well. If we were running on a daily time step, we couldn't evaluate either of those standards because you just get one DO concentration per day instead of 24. So you need the temporal resolution of an hourly time step. You also need to include the critical processes in your model, including photosynthesis, that's a source of oxygen. Respiration is a sink. Reaeration is a sink during the day, but a source at night. These other processes are also sinks. They're important, so you need to include them. And so I'll go back to the Little Cobb TMDL. You see here we've got this violation. We're going below 5. So I took the HSPF model and I reduced the phosphorus loading, and it turns out if I reduce the phosphorus loading by about 40%, I can reduce algal growth and death by 32%, and that will be enough to keep this minimum DO from going below 5. So myself and my colleagues wrote that up. You know, that became the TMDL. So that was the reduction needed to meet the dissolved oxygen TMDL. And I sent that off to EPA and they approved it, and they were happy. And then that makes me happy. And we've got another TMDL off the books and done. So, you know, that's a positive thing for myself personally. Lastly, I do want to say that we use HSPF to support stressor identification studies, and they're a little bit different because biologists don't care about loads. They care about the concentrations that the fish are being exposed to. So I was able to use the HSPF model for some of the upstream reaches that they were interested in. Yeah, these are this is a headwater stream. And along the vertical axis, you have the years. Across the bottom here, I have the months. And the biologist wanted to know, when are the nitrate concentrations above 3 and above 5 in this headwater stream? And so where you have the light color, it's above 3. Where you have the dark bar, it's above 5. But this was also the biologist found this useful in her work. And lastly, this is a map of where we have HSPF models in the state. And I should say this is a map of where we have at least one. So the dark blue, we have HSPF, at least one model of the HSPF. And even though we have HSPF models, will never be done because it's a continuous simulation model, and most of our models start in 95 and they run through 15 or 18, but will always be appending at the end of the time series the most recent time period. So these models will never be sort of completely finished. We'll always be adding on to the end. And if we have a new impairment, we will update the segmentation. Obviously, when we extend the models, we will check the flow and the water quality calibration, and we'll make adjustments if necessary. And that's all I have. So thanks very much for your attention and patience. And hopefully I didn't bore anyone too badly. I know it might not be the most exciting topic for a Friday afternoon, but thanks very much.
Thank you, Chuck. Thank you very much, Chuck, for that presentation. I think you get a really good background on just general concepts of modeling and why do we do models, and what kind of models are there, and what's the complexity of them, and what value there are, and the fact that there's no just one model. So I think it really helps. The effort that's going on in the state with models, I think, gives everybody a big appreciation for the effort that's going into this. So with that, let's see if there's some questions that anybody might have.
I have a question for you, Chuck. What are some of the main challenges you face in using HSPF, and some of the main controversies that you faced as you were going through this whole process?
Well, clearly, what I stress about the most is the point source permitting, because you're basically telling someone you have to spend $3 million instead of $1 million because of what our model says. And when you're dealing with non-points, it can be controversial, but we don't have any regulatory teeth with non-points. So, when it comes to non-point, we're not requiring other people to spend their money. But with the point source, it's, you really, really, really have to do your due diligence on the river reaches that affect, the reaches that are affected by where the point source discharges. So you really have to try and do as much sampling, get the different speciation of phosphorus straightened out. And So I don't know if if I'm exactly answering your question, but I think the biggest challenge is just from a political standpoint is the point sources, because, you know, they don't want to spend money on upgrading a system necessarily. And we're telling them they have to, and they want to know how we came up with the answer. And they go, you tell them it's a model, and they're like, well, they want to pick at it. They want to, you know, give me a copy of it. They want to challenge it in court. So that's the most challenging. I mean, the non-point can be challenging, but again, we don't force people at the current time. We don't force people to spend money on non-point through our regulatory authority anyway.
John, I got a question. John, can you hear me?
Yeah, go ahead, Satish.
Say,
Go ahead.
Chuck, this is Satish Gupta. I thought several of your slides early on that give out pretty good rosy picture of using the models. And one of the limitations that you didn't point out in there was that you already have an understanding of the watershed that you are going to be looking at when you say, well, only have the complexity that you need and not any more than that. And I think that's been one of the limitations of the MPCA's work. You know, going back to 1994 when the MinRap came out, you guys didn't want to buy. There was a bank erosion, or phosphorus was coming in the Lake Pepin was not from agriculture. And it has been a fight over the last 10, 15 years to get you guys to there. And even then, some of your functions are not looking at the processes of how the banks are sloughing and so on. So I think maybe you got to be careful when I think your presentation is good for the student who want to use model, but models are only good as much as you understand and not what you don't know. And this has been a problem here in Minnesota.
Yeah, no, I think you make an excellent point, and I think when it comes to sediment in particular, there is, you know, whatever watershed model you're using, often if the modeler assumes it's all coming from fields and using US LE type processes, yeah, you won't have an accurate model. So really it's beholden to the modeler to ask himself, where is the sediment coming from? And yeah, if we have sediment, some watersheds, we have a lot coming from bluffs, you know, up in the boundary waters, not nearly as much, but I think it's really beholden on the modeler to have sort of sediment calibration targets and say, because HSPF is not going to tell you, or SWOT I don't think is going to tell you how much is coming from bluffs. You have to do your own research project to determine that, and you need to do the research before you build a model, and then make sure the research is incorporated into the model.
But do you think some of your consultants do that? They don't even go to the field or have any understanding?
Before we build a model, or before they construct a model, we come up with sediment targets for every reach. So for instance, in the LeSueur, those uplands in the south, we don't think a lot of sediment is coming from bluffs in those up above the Nick zone. But in the Nick zone themselves, most of the sediment, the overwhelming majority of sediment, is coming from bluff collapse. So that's something that's a requirement in the work order, is you have to get together and talk about how much for every sub-watershed, how much sediment is coming from channel widening, how much sediment is coming from bluff collapse, how much sediment is coming from ravine incision, and how much is coming from fields. So that is a requirement for when these models are originally constructed.
Yeah, but I think keep in mind, I don't want to belabor this point that, there are still things that you guys don't know and you guys are assuming you know it. And that's where I think people don't believe much of the predictions from these models. Anyway, I'll let it go and have other people ask you the question. Thank you for answering my questions.
Yeah, well, and that's very fair. I mean, the main reason we're using this is we have to do sediment TMDLs and sediment TMDLs and dissolved oxygen TMDLs, and we use HSPF, and EPA approves them. So as long as EPA keeps approving them, we're going to keep using them. And we recognize that we have a lot of critics out there and a lot of skeptics, and that's everybody's entitled to their opinion. But we have a mandate we need to meet, and this is the tool that we're using to meet that mandate. And as long as EPA is approving our work, we're going to keep doing it the same way.
I see there's a question on the chat.
I was wondering, obviously there's a lot of different opinions about these models and how they work and stuff. And so once you go through this process of defining the TMDL and going through the model, do you how often is it part of your process that you go into court in if people are fighting these point source polluters are fighting this? Do you get involved in that, or is it you handed it off to the EPA? Now they deal with those legal fights and everything like that.
No, the state of Minnesota. So it's basically staff and management and attorneys. So really it's the staff like myself who are involved, and then my bosses, and then we have attorney, the Pollution Control Agency has attorney generals that work directly for our agency. So we work with the city who's unhappy with their permit limit, and then sometimes we settle out of court. A lot of times we do, and sometimes we go to court.
So you're obviously the expert on, if you make the model, you're the expert on the model. So, I mean, these attorneys and stuff, obviously they have to have some sort of background in that, but how do you clear that middle ground where you make sure everybody, understands how the model's working, why it's working, all that kind of stuff for the people that, don't agree with the results you came up with?
Yeah, that's a good question. I think in many cases, and a lot of what they want more time, and I think by fighting that gets them more time. But I think we have phosphorus limits on almost all of the major facilities, not all, but almost all. And I think when you show them that, the city of Rochester's doing it, the city of Mankato's doing it, the metro area is doing it, St. Cloud is doing that, usually eventually they fall in line, or the judge rules that they should fall in line.
Thank you.
Sure. I mean, yeah, they will fight it, and sometimes they drop it, and sometimes they don't.
Yeah, I have a question from chat. It says, I'll try to get this correct. I believe there are researchers looking at using water quality monitoring data to calculate a changing TMDL in real time based on the actual water quality data, instead of having a fixed TMDL for a few years. What are your thoughts on that? And do you think it's feasible for municipal agencies to use in the future?
Yeah, I am aware. I believe in South Dakota, there's some of that where they're basically calculating a TMDL in real time using, you know, data collected in real time. I'm not really familiar with that. I mean, it sounds interesting and maybe would be a good way to go, rather than using time periods that people think are too old. But yeah, I don't know enough about that technology to really to give a educated and informed opinion, but I have heard about it.
It's actually something new to me also, Chuck, and we teach a class on impaired waters. And I'll have to bring this one up so that we can maybe incorporate some of that in the course. Thank you. Other questions? I might ask Chuck, because of my own experience working with you recently with one of my graduate students, about the availability of calibrated HSPF models. You've got all these watersheds and you've already got these, you know, I mean, there's been a lot of money spent on calibrating them for these watersheds. So maybe you could just mention something about if there is a student that they don't have to go out and start from scratch, if they're going to use it at the scale that has already been developed.
Yeah, no, they are available, and whenever I get a request, I try to get the model out within 24 hours. So they're built with taxpayer money, so anybody who wants them is welcome to them. Like you said, in terms of calibration, I mean, some models are outstanding, and some other models, sometimes we might have a land use that's not as calibrated as we'd like, because there might be a land use that's 0.5% of the watershed, and it might not be parameterized the way it should, but it doesn't really show up because it's such a small percentage. So there are things like that I catch. You know, I try to go through everything. It takes a lot of time, and it seems like I'm always reacting and putting out fires and being proactive. So there are things like that, you know, in an agricultural area that has less than 0.5% forest, sometimes there's some issues with the forest. But, you know, clearly when you have the dominant land uses are all, you know, well parameterized, but sometimes you get some minor ones. So, you know, there's certainly no model is perfect. And I think for the most part, they're good for what we're using it for. They might not be good for what you need to do, but I think they're helpful for what we need to do. But definitely any student who wants a model is welcome to it, or any person, period. So you can, you know, they can email you or they can email me, and you know, usually they're obviously too big to send as an email attachment, so we'd have to, you know, either I could upload it to the FTP site of the MPCA, or if people have a SharePoint or a Dropbox, we can do it that way. But you know, I do get a pretty steady number of requests for models, and like I said, I always try and promptly meet them. You know, you can ask Victor about that. You know, he can comment on it.
Your help has been excellent there. Other questions? Okay, not hearing any. I want to thank you, Chuck. If everybody can kind of give him a thumbs up. Really appreciate the presentation today. It was excellent.